December 1944. Lieutenant Colonel Takeshi Yamada crouches in a captured American supply depot somewhere in the Philippine jungle, holding what looks like a mechanic's grease gun. The metal is so thin he can feel it flex under his fingers. 8 pounds, stamped steel, seam welded together like something a child made in a garage. Yet his intelligence reports say the Americans are carrying these by the thousands. He strips it down in minutes. No precision parts, no hand fitting, just crude stamped metal that slides together with tolerances his ordnance factories would reject as defective. Then he sees the production stamp, May 1944. 7 months ago. Japan has already lost this war. Yamada's realization in that Philippine supply depot isn't isolated. It's happening everywhere Americans advance. Manila, Iwo Jima, Okinawa, Saipan. Every captured position reveals the same devastating truth. Warehouses full of equipment that shouldn't exist at these prices, in these quantities, produce this quickly. 3,000 miles north, in a Tokyo conference room, Major General Yoshio Kazuki of the Army Technical Bureau is compiling reports from ordnance officers across the Pacific. The numbers aren't just bad, they're apocalyptic. The M3 grease gun, that crude stamped metal weapon officers keep describing in their reports, has been produced at rates Japan cannot comprehend. Guide Lamp Division, a General Motors subsidiary in Anderson, Indiana, that made automobile headlights before the war, has manufactured over 606,000 M3 submachine guns between May 1943 and August 1945. Japan, by contrast, has produced approximately 17,000 Type 100 submachine guns in the entire war. The production ratio is 35-1. Kazuki slides another report across his desk. Machine guns. The Americans have produced 390,000 M1919 Brownings. Japan has manufactured 45,000 Type 92 machine guns. That's a 9-1 disparity. Tanks. Sherman production, 49,000 units. Japanese medium tank production, approximately 2,000 units. A 24-1 gap. Time, 0.5s. Aircraft tell the same story, 297,000 American planes versus 76,000 Japanese. But those disparities can be explained by industrial capacity, by America's larger factories and greater resources. The M3 grease gun represents something more troubling. It's not just that Americans can build more weapons, it's that they've fundamentally reimagined how weapons should be built. The cost analysis makes Kazuki's hands shake. The M3 costs $20.94 per unit. Intelligence estimates place the Japanese Type 100's manufacturing cost at $60 to $100 per unit, 3 to 5 times more expensive. But cost isn't even the most devastating metric. The M3 requires 3.7 man-hours of labor per weapon. The Type 100 requires approximately 18 hours. American workers are producing submachine guns nearly 5 times faster than Japanese craftsmen. The mathematics translate directly to battlefield reality. For the cost of arming one Japanese regiment with automatic weapons, America can arm an entire division. And they're doing exactly that. By late 1944, approximately 35% of American frontline infantry units carry submachine guns. In the Japanese army, that figure hovers around 3%. The human cost of this firepower gap is written in blood across every island battlefield. In the Philippines campaign alone, over 200,000 Japanese soldiers have been killed or wounded against 60,000 American casualties. Japanese infantry armed with bolt-action Arisaka rifles face American troops, where even support personnel carry automatic weapons. American ordnance officers estimate their forces maintain a 5 to 10 times close combat firepower advantage per soldier. At Peleliu, Japanese defenders watch in horror as American Marines advance with what seems like unlimited automatic fire. At Iwo Jima, Japanese machine gun positions, laboriously hand-carried into fortified caves, are suppressed by sheer volume of American firepower. The carefully aimed, conserved fire that Japanese training emphasizes becomes irrelevant when facing enemies who can afford to spray bullets. But the strategic implications extend beyond any single battle. Kazuki understands what his superiors are reluctant to acknowledge. This isn't a gap Japan can close. Time 0.5s. Even if Japanese factories adopted American methods tomorrow, which they can't because the entire industrial infrastructure is built around precision machining rather than stamping, there's no time. American B-29s are firebombing Japanese cities. Industrial capacity is collapsing. The raw materials needed for manufacturing don't exist. The production timeline on that M3 Yamada examined May 1944, just 7 months before he held it, represents the knife twisting in the wound. American factories aren't just producing weapons faster. They're producing weapons that didn't exist a year ago, designed from scratch for rapid manufacturing and flooding battlefields with them in quantities that would take Japan decades to match. A report from Okinawa lands on Kazuki's desk. A captured American supply manifest lists weapons delivered to a single Marine regiment, 147 M3 submachine guns. That's more automatic weapons than some entire Japanese divisions possess. The Americans are using submachine guns as standard issue. The Japanese are rationing them to elite units. The pattern repeats across every category of military equipment. Ammunition expenditure, Americans fire 6,000 rounds per enemy killed. Japan fires approximately 500 rounds. Not because Japanese marksmanship is better, because Japanese factories can't produce ammunition at American rates. Artillery shells, mortar rounds, grenades, in every category, American production exceeds Japanese output by factors ranging from 5 to 1 to 50 to 1 depending on the weapon system. Something fundamental has changed in how modern wars are won. Victory no longer belongs to the nation with superior tactics, better training, or greater fighting spirit. Victory belongs to the nation that can produce more weapons, faster and cheaper than the enemy can destroy them. And Japan's entire military philosophy, precision craftsmanship, hand-fitted quality, martial excellence, has collided with American industrial mass production. The collision is catastrophic. Kazuki closes the reports. He knows what they mean. Japan has already lost this war. Not because Japanese soldiers won't fight, they'll fight to the death, as they're doing on every island. Not because Japanese weapons are inferior, the Type 100 is arguably a more refined weapon than the crude M3. Japan has lost because American factories can produce 35 crude weapons in the time Japanese craftsmen produce one refined weapon. And in modern warfare, good enough produced rapidly beats excellent produced slowly. The question that haunts every Japanese ordnance officer examining captured M3 grease guns is simple and devastating. What fundamental principle of weapons manufacturing have the Americans discovered that Japan missed? What counterintuitive truth has enabled them to produce functional automatic weapons at 1/5 the cost and 1/5 the time? The answer exists. It was predicted. It was even documented in warnings Japanese officers wrote years earlier. But by December 1944, understanding comes too late to matter. The invisible enemy isn't the Americans. It's a manufacturing philosophy so deeply embedded in Japanese military culture that questioning it is like questioning gravity. For centuries, Japanese craftsmanship has meant one thing: perfection through meticulous handwork. Sword-making traditions requiring master smiths spending months on a single blade. Woodworking demanding perfect grain alignment. Metalwork celebrating the beauty of hand-finished surfaces that gleam like mirrors. When Japan industrialized in the late 19th century, modernizing its military to compete with Western powers, these values transferred directly to weapons manufacturing. A weapon should be crafted, not merely produced. Quality meant tight tolerances, components fitted so precisely that inserting a bolt into a receiver required careful alignment. It meant hand finishing, each weapon individually adjusted until it functioned perfectly. It meant material quality, thick steel receivers machined from solid billets, heavy components that felt substantial in the hand. This philosophy worked brilliantly for small-scale production of complex systems. The Nambu Type 14 pistol represented excellent engineering. The Arisaka rifle was reliable and accurate. The Type 100 submachine gun, when it finally entered production in 1940, embodied Japanese ordnance values: precision-machined steel receiver, hand-fitted bolt, individually adjusted to function smoothly. Each weapon took 18 hours of skilled labor to manufacture. Each cost an estimated $60 to $100, and Japanese ordnance officers believed this approach was superior. The math seemed obvious. More material equals stronger weapons. Tighter tolerances equal more reliability. More hours of skilled labor equal better results. A precision-machined steel receiver should outperform thin stamped metal. A hand-fitted bolt should be more reliable than loose-tolerance assembly line parts. But there's a counterintuitive physics principle at work that Japanese engineers missed entirely. Functional reliability in mass-produced weapons depends on design for manufacturing, not manufacturing for design. The Americans discovered something revolutionary: if you design a weapon specifically for stamped metal construction from the ground up, not simplify an existing precision design, but start from scratch optimizing for what stamping does well, you can achieve equal or superior reliability with dramatically reduced cost and time. The technical explanation reveals why Japanese intuition catastrophically failed. Traditional gun design starts with the ideal weapon, then figures out how to manufacture it. You envision the perfect submachine gun: smooth functioning, tight tolerances, precision-fitted parts. Then you build manufacturing processes to achieve that vision. This requires precision machining to achieve tight tolerances. Precision machining requires skilled machinists. Skilled machinists work slowly. Slow work limits production speed. The American approach, pioneered by George Hyde and Frederick Sampson, inverts this entirely. Start with available manufacturing capability. General Motors has automotive stamping presses designed to stamp car body panels, then design a weapon optimized for those specific capabilities. The M3's receiver isn't two stamped pieces because it's cheap. It's two stamped pieces because that's what existing GM equipment can produce most efficiently at highest volume with minimal retooling. The crude seam weld running down the M3's receiver isn't a compromise. It's the optimal solution for rapid production. Those loose tolerances that make Japanese inspectors reject components. They're intentional. The M3 is designed so that parts with loose tolerances still function reliably because the design itself compensates. Consider the receiver. A traditional machined receiver starts as a solid steel billet, weighing perhaps 15 pounds. Machinists spend hours boring out the interior, creating the cylindrical space where the bolt travels, machining mounting points for components. When finished, the receiver weighs maybe 3 pounds. 12 pounds of steel became machine shop waste. The process consumed 6 to 8 hours of skilled labor. The M3's receiver starts as two flat sheets of 0.060-inch steel. Each sheet is stamped, one press stroke taking perhaps 10 seconds, into a half-cylinder shape. The two halves are positioned in a fixture and seam welded together in under 3 minutes. Total steel used, equivalent to 2 pounds. Waste, negligible. Labor time, under 5 minutes for both stamping and welding. The receiver that took 6 to 8 hours to machine now takes 5 minutes to stamp and weld. But here's the counterintuitive truth Japanese engineers cannot accept: that thin-walled stamped receiver is actually more reliable than the machined version. Because the stamp design has fewer internal corners where stress concentrates. Because the seam weld, while crude, is actually stronger than the surrounding metal. Because the whole assembly flexes slightly under stress rather than cracking. The instinct trap kills Japanese production capacity. When Japanese engineers examine captured M3s, and they do thoroughly in ordnance laboratories across occupied territories, they see the solution. Stamped metal construction. They understand it intellectually. Some even write reports recommending adoption of stamping techniques. But they can't implement it. Because their entire manufacturing infrastructure is built around precision machining. Their factories contain machines for boring receivers from solid steel billets, not stamping presses for sheet metal. Their workforce consists of skilled machinists, trained in hand-fitting and precision measurement, not assembly line workers who operate stamping equipment. Their quality control standards explicitly reject the loose tolerances that make stamped weapons producible at scale. To adopt American methods would require scrapping Japan's entire manufacturing philosophy and infrastructure. In 1944, with American bombers targeting industrial cities, with raw material shortages crippling production, with skilled workers conscripted for military service, such a transformation is impossible. But even more insidious than practical constraints is the psychological barrier. Japanese military culture cannot accept that crude is superior. When an ordnance officer picks up an M3 grease gun, every sensory input screams inferior weapon. The thin-walled receiver feels flimsy compared to a solid machine Type 100. The loose-fitting bolt rattles when you shake it. The stamped trigger housing looks unfinished, like someone forgot to polish it. The seam weld running down the side resembles something a mediocre welder made in a garage. Their training says precision engineering produces better weapons. Their experience handling finely crafted Japanese firearms reinforces this. Their decades of expertise all confirm that tight tolerances, heavy materials, and hand-fitting equal quality. The idea that a weapon costing 1/3 as much and requiring 1/5 the manufacturing time could be functionally equivalent, let alone superior, is literally unthinkable within their conceptual framework. It's not stupidity. It's not ignorance. It's cultural conditioning so deep it's become invisible. Japanese officers attempt multiple solutions, all of which fail because they maintain the fundamental philosophy. In 1944, facing production shortages, Japanese ordnance introduces the Type 144, a simplified variant. They eliminate the adjustable rear sight, replacing it with a fixed peep sight. They remove the bayonet mount. They use rougher finishing, skipping the final polishing steps. Production time drops slightly. But the Type 144 still requires hand-fitted internals, still uses machined steel receivers, still demands skilled labor. Perhaps 7,000 are produced in the war's final year. Many never reach frontline troops before surrender. Japanese soldiers eagerly adopt captured American weapons when available. Thompsons, M1 Garands, M1 carbines, anything they can find ammunition for. But this doesn't solve the production problem. Japan can't manufacture .45 ACP or .3006 ammunition at scale. Captured weapons become battlefield curiosities, not solutions. By mid-1945, desperate Japanese ordnance factories produce last-ditch substitute weapons using whatever materials are available. But even these emergency designs maintain hand-fitting philosophy, just with worse materials. They produce fragile weapons slowly rather than robust weapons quickly. The tragic irony, Japanese metallurgical knowledge is excellent. Their understanding of firearms mechanics is sophisticated. Individual Japanese engineers understand stamped metal construction as well as American engineers. But understanding isn't enough. Institutional structure, cultural values, manufacturing infrastructure, and psychological frameworks all prevent Japan from implementing what they intellectually comprehend. By December 1944, Japanese ordnance officers examining M3 Grease guns understand they're looking at proof of their defeat. Not because it's a better gun. The Type 100 is arguably more refined, more accurate, more pleasant to shoot. They've lost because American factories can produce 35 M3s in the time Japanese factories produce one Type 100. The invisible enemy is the manufacturing philosophy itself, the belief that weapons quality correlates with manufacturing precision, that craftsmanship trumps mass production, that more expensive means more effective. The Americans proved that for infantry weapons, good enough produced rapidly beats excellent produced slowly. And there's no solution available to Japan in 1944. The war is being lost in American factories, not on Pacific battlefields. The decisive weapon isn't the M3 Grease gun itself, it's the manufacturing philosophy that produced 622,000 of them in 28 months. There is no single forgotten prophet who warned Japan about American manufacturing superiority before Pearl Harbor. But there was a warning so stark, so obvious, that ignoring it qualifies as willful institutional blindness. March 1942. Major Kijiro Nambu, nephew of famous pistol designer Kijiro Nambu, sits in a Tokyo office writing a report that will be filed and forgotten for 2.5 years. Through German allies, Japanese intelligence has obtained detailed specifications of the British Sten submachine gun, adopted by Britain in 1941. And what Nambu sees in those specifications terrifies him. The Sten costs under $10 per unit, less than 1/6 what Japanese intelligence estimates for any Japanese weapon. It uses stamped metal construction throughout, receiver, barrel housing, magazine housing, all stamped from sheet, metal and welded together. It requires minimal machining. Only the barrel, bolt, and firing pin are precision-made. British factories are producing thousands monthly using semi-skilled labor, many of them women with no firearms manufacturing experience. The Sten represents proof that stamped metal submachine guns work in combat. British troops are carrying them across North Africa. And if Britain, with its relatively limited industrial capacity compared to America, can produce functional automatic weapons at $10 per unit, what will American industrial might achieve? Nambu's report to the Army Technical Bureau, obtained from post-war archives, states, British Sten gun demonstrates enemy capacity to produce functional automatic weapons at unprecedented low cost through stamped metal construction. If American industrial capacity applies similar methods at scale, Imperial Japanese Army may face 10-to-1 or greater disadvantage in automatic weapons distribution. Recommend immediate research into simplified production methods. Nambu goes further. He calculates that even with Japan's limited industrial capacity, adopting stamped metal construction could increase Type 100 production 5-fold while reducing costs by 60%. He proposes that Japan could arm entire divisions with submachine guns by 1944 if production methods shift immediately. His analysis is remarkably accurate. He's essentially predicted the M3 Grease gun's manufacturing approach 2 years before America designs it. The institutional dismissal is swift and comprehensive. Senior Army ordnance officers view the Sten as evidence of British desperation, not innovation. The crude appearance offends Japanese aesthetic sensibilities. One general's response, documented in post-war interrogations, dismisses the Sten as something appropriate for colonials and conscripts, not soldiers of the Imperial Japanese Army. Another officer writes in the margin of Nambu's report, "We will not arm Japanese soldiers with garbage." The manufacturing inertia proves equally immovable. Existing ordnance factories have invested millions of yen in precision machining equipment. Converting to stamped metal production would require scrapping lathes, boring machines, precision grinders, equipment that represents decades of capital investment. Factory managers resist. Converting production would halt current manufacturing for months during retooling. With war expanding across Asia and the Pacific, no one wants to explain to headquarters why weapons production stopped. Quality control standards present another barrier. Japanese military specifications explicitly prohibit the loose tolerances the stamped manufacturing produces. Ordnance inspectors are trained to measure component tolerances to thousandths of an inch. A stamped component that varies by 5 thousandths would be rejected automatically, even if it functions perfectly. Changing these standards would undermine decades of quality control training and doctrine. But the deepest reason for dismissing Nambu's warning is strategic overconfidence. In March 1942, Japan is winning. The Philippines have fallen. Singapore, the great British fortress, has surrendered. Burma is falling. Japanese forces control resource-rich territories across Southeast Asia and the Pacific. Why abandon proven manufacturing methods when winning? Why risk production disruption when current weapons are defeating enemies? The urgent need for five-fold production increases isn't apparent when Japan controls conquered territories and faces apparently inferior enemies. American forces haven't yet demonstrated the industrial mobilization that will bury Japan in materiel. In March 1942, Nambu's warning seems theoretical, even alarmist. His report is filed. He's reassigned to artillery projects. The Type 100 continues limited production using traditional precision manufacturing methods. Japanese military leadership concludes that quality will overcome quantity, that superior training, fighting spirit, and precision weapons will defeat American numbers. This conclusion proves catastrophically wrong. The rediscovery comes too late to matter. October 1944. After the devastating defeat at Leyte Gulf, after Philippines' campaign casualties mount beyond projections, General Yoshijiro Umezu, Chief of the Imperial General Staff, orders a comprehensive review of armaments production. Why is Japanese industry failing to equip troops adequately? Staff officers sift through 2 years of reports, recommendations, and analyses. Someone finds Nambu's March 1942 report buried in archives. The reaction, documented in post-war testimonies, is stunned silence. One staff officer reportedly said, "He told us. 2.5 years ago, he told us exactly what would happen. Every prediction Nambu made has come true. Britain produced stamped submachine guns by the tens of thousands. America, studying British methods, designed the M3 grease gun, even cheaper, even simpler to manufacture than the Sten. American production has exceeded Nambu's worst projections. The 10-to-1 disadvantage he warned about. Reality is 35-to-1. By October 1944, implementing Nambu's recommendations is impossible. Japan lacks raw materials, industrial capacity, and time to convert manufacturing philosophy. American B-29s are firebombing Japanese cities, targeting the very factories that would need retooling. The industrial infrastructure necessary for mass stamping barely exists. Skilled workers have been conscripted for military service or killed in air raids. The Philippines are being retaken. Iwo Jima and Okinawa loom ahead. The war is lost. Nambu's warning, which could have been heeded in early 1942 when Japan had time, resources, and industrial capacity to shift manufacturing philosophy, has been validated at the cost of hundreds of thousands of lives. Major Nambu survives the war. In post-war interviews with American occupation forces, he demonstrates detailed understanding of American manufacturing principles. He's asked why his warnings were ignored. His response, quiet and devastating. "We believed our way was superior. By the time we learned otherwise, it was too late to change." The institutional failure wasn't lack of knowledge. Japan knew stamped metal construction worked. The British proved it in 1941. Japan knew American industrial capacity was vast. Pre-war intelligence documented it. Japan even had officers who understood the implications and recommended action. The failure was institutional pride preventing Japan from learning from inferior Western methods. until battlefield defeat made the lesson undeniable. By then, understanding came too late to save lives or change outcomes. The war's outcome was decided not on any battlefield, but in a Tokyo office in March 1942 when a major's prescient warning was filed and forgotten. October 1942, Aberdeen Proving Ground, Maryland. Time 0.5s. George J. Hyde sits in a cramped workshop sketching what will become the most influential weapon he'll never receive credit for designing. He's 54 years old, a German immigrant who arrived in America 15 years earlier with machinist skills and no formal engineering credentials. Most people have never heard his name. After this war ends, most still won't. But Colonel René Studler, Chief of Research and Development for Army Ordnance, has specifically requested him for this project. Hyde has a reputation among people who matter. He designs weapons that can actually be manufactured, not weapons that look impressive on paper. Hyde's background gives him a unique perspective. Born in Apfingen, Germany in 1888, he learned precision machining in German workshops, where tolerances were measured in thousandths of millimeters, and craftsmen took pride in mirror-polished finishes. When he immigrated to America in 1927, he brought those skills to Griffin and Howe, working his way up from shop foreman to eventually co-owning Leonard and Hyde, a firearms company in New York. But somewhere along the way, Hyde learned something that separated him from traditional gunsmiths. He learned that achieving function through simplicity was genius, not compromise. That weapons soldiers carried into combat needed to work reliably, not win craftsmanship awards. That in modern warfare, having enough weapons mattered more than having perfect weapons. Now Studler has given him an impossible challenge. Design a submachine gun that can be produced for under $30 using automotive manufacturing techniques. Something to replace the Thompson submachine gun, which costs $45 per unit, even in its simplified M1A1 variant, and requires extensive machining. Something that can be produced by the hundreds of thousands. Hyde studies the available examples. The German MP40 uses some stamped components but maintains complex precision-machined parts in critical areas. It's an evolution of traditional design, simplified but not revolutionary. The British Sten sacrifices everything for cheapness. It costs under $10, but British troops despise it, calling it crude, unreliable, dangerous. The Thompson is excellent, but absurdly expensive and slow to produce, requiring extensive hand-fitting of precision machine components. Hyde recognizes the fundamental problem everyone else missed. Time 0.5s? They're all trying to simplify existing designs. Take a complex weapon and figure out which parts can be made cheaper. But what if you started from scratch? What if you designed specifically for stamped metal production instead of trying to adapt precision designs for cheaper manufacturing? His insight, sketched in his October 1942 notebook, is deceptively simple. A submachine gun receiver doesn't need to be machined from solid steel. It can be two stamped halves seam welded together. The receiver is just a tube. It holds components. It doesn't experience the high pressures that a barrel experiences. It doesn't require the precise tolerances that a bolt requires. It just needs to be a strong, cylindrical space where the bolt can travel back and forth. Why machine a tube from a 15-pound steel billet when you can stamp two half-cylinders from sheet metal and weld them together? This sounds absurdly simple. When Hyde presents the concept to Studler, the colonel's initial reaction is skeptical. That's too crude. It won't be accurate enough. Hyde's response reveals his genius. It doesn't need to be accurate. It needs to function. The insight represents a conceptual revolution. Separate weapons components into two categories, those requiring precision, barrel, bolt, firing pin, and those just needing structural integrity, receiver, trigger housing, stock. Design each category for its optimal manufacturing method. Precision components get traditional machining. Structural components get stamped from sheet metal. The resistance is immediate. Senior Army Ordnance officers, trained in precision weapons designed for decades, dismiss the concept. One calls it something a plumber welded together in a basement. When Hyde produces early prototypes in November 1942, receiver warping from welding heat gives critics ammunition to declare the concept fundamentally flawed. This is where Hyde's partnership with Frederick W. Sampson becomes crucial. Sampson is chief engineer at General Motors' Inland Division. He doesn't know much about firearms, but he knows everything about automotive stamping and mass production. He knows how to design stamping dies that minimize warping. He knows how to sequence welding operations to control heat distortion. He knows how to use assembly fixtures to maintain dimensional accuracy during production. Together, they solve the manufacturing problems the military critics said were unsolvable. By December 1942, they have 5 working T-20 prototypes. The weapons function flawlessly in Aberdeen Proving Ground testing. They actually outperform Thompson's in mud and dust tests because the simpler design has fewer places for debris to jam mechanisms. The cost estimate, $20.94 per unit. The manufacturing time estimate, 3.7 man-hours. These numbers are so dramatically better than anything else available. Thompson M1A1 costs $45 and requires 8 to 12 hours manufacturing time that Army leadership must pay attention. Cost isn't just about money. It's about how many soldiers can be equipped with automatic weapons. It's about how quickly production can scale when America enters full wartime mobilization. On December 12, 1942, the U.S. Army officially adopts the weapon as the United States submachine gun Calamis .45 M3. It's one of the fastest adoption timelines in military history, concept to official adoption in just 10 weeks. But adoption doesn't mean immediate success. Production at General Motors' Guide Lamp Division in Anderson, Indiana, begins in May 1943. The division normally manufactures automobile headlights. Now it's making submachine guns. And immediately, problems emerge. The seam welding causes more receiver warping at production scale than prototypes suggested. Stamping dies wear faster than predicted, creating dimensional variations. Quality control inspectors, trained their entire careers on precision weapons, initially reject half the receivers as defective because they don't meet traditional tolerances, even though they function perfectly when tested. Hyde and Sampson's persistence during mid-1943 proves critical. They revise welding sequences to distribute heat more evenly. They redesign stamping dies to compensate for predicted warping. They implement assembly fixtures that maintain alignment during welding. Most importantly, they convince quality control to test function rather than measure tolerances. If a receiver looks crude but passes function testing, cycling the action thousands of times. Without failure, it passes inspection. By July 1943, monthly production reaches approximately 7,000 units. Still far below projections, but climbing steadily. By December 1943, production hits 10,000 monthly. The manufacturing kinks are being resolved through systematic problem solving. The real experimental proof comes from battlefield testing. June 6, 1944, D-Day. Paratroopers from the 82nd and 101st Airborne Divisions hit the ground in Normandy carrying M3 grease guns. Many are skeptical. The weapon feels too light compared to the Thompson, 8 pounds versus the Thompson's 10.8 pounds. The thin stamped metal seems fragile. Soldiers question whether it will function when lives depend on it. Then combat starts. And the M3 works. Reliably. Even caked in Normandy mud. Even after being dropped during parachute jumps. Even after days without cleaning in the chaos of hedgerow fighting. The low cyclic rate, 350 to 450 rounds per minute, compared to the Thompson's 650, proves advantageous. Soldiers can actually control single shots through trigger manipulation. In close-quarters combat, the lightweight and low recoil become assets, not liabilities. After-action reports from July 1944 shift from skepticism to acceptance. One report from the 101st Airborne states, M3 submachine gun performed exceptionally. Lightweight advantageous for paratroop operations. Low cyclic rate enables accurate fire. Soldiers initially complained about appearance, but no functional problems reported. The before and after statistics are dramatic. M3 malfunction rate 2.1 failures per 1,000 rounds fired. Thompson M1A1 3.7 failures per 1,000 rounds. The crude weapon isn't just cheaper and faster to produce, it's actually more reliable in combat conditions. Word spreads through military channels. Armored divisions request M3s because the compact design fits tank crew compartments better than Thompson's. Tank commanders report that crews can egress from disabled vehicles faster carrying the shorter, lighter M3. Time 0.5s. In the chaos of tank warfare where seconds determine survival, this matters. Ranger and commando units adopt M3s for their lightweight during long-range patrols. By late 1944, demand exceeds supply. Production at Guide Lamp Division ramps dramatically, 28,600 units monthly, 4 times the mid-1943 rate. The manufacturing problems have been systematically solved through iterative refinement. An improved M3A1 variant is introduced in December 1944, incorporating field feedback, simplified cocking mechanism, enlarged ejection port, elimination of the cocking handle in favor of a finger notch on the bolt. The timeline of expansion shows exponential growth once manufacturing processes mature. 1943, 85,130 M3S produced. 1944, 343,372 M3S produced. 1945, 178,192 M3S plus 15,469 M3A1S produced. Total production by August 1945, 622,163 units. Average cost, $20.94 per unit. Average manufacturing time, 3.7 man-hours. The grassroots solution, designed for manufacturing rather than manufacture for design, has validated itself through battlefield performance and unprecedented production efficiency. But Hyde receives no public recognition during the war. His name doesn't appear on the weapon. Most soldiers carrying M3S never know who designed the grease gun they're betting their lives on. Hyde files patent number 2,403,306 on May 1, 1944, co-inventor with Sampson. The patent is classified. He receives no royalties. The military establishment credits Army Ordnance collectively. After the war, Hyde returns to private firearms design, working on various projects, remaining largely anonymous in the public consciousness. He dies December 2, 1963, at Adelphi Hospital in Brooklyn. His obituary in the New York Times runs 4 sentences. It doesn't mention the M3 grease gun. It doesn't mention the 622,163 weapons produced using his design. It doesn't mention that his manufacturing philosophy influenced every subsequent military weapon worldwide, but his insight that weapons should be designed for how they'll be manufactured, not manufactured to match ideal designs, becomes the foundation for modern military procurement worldwide. Every stamped receiver weapon produced since 1943 is his conceptual descendant. His son, George Hyde Jr., inherits his father's technical papers. In a 1986 interview with a firearms historian, Hyde Jr. says something that captures his father's genius. "My father knew the gun was crude. That was the point. It worked because it was crude, not despite it." The M3 grease gun's battlefield success forces a systematic transformation in American military manufacturing doctrine that extends far beyond a single weapon. By mid-1944, Army Ordnance recognizes that Hyde and Sampson's approach, designed for manufacturing, applies to all military equipment. The principle becomes doctrine. Weapons should be designed to exploit existing manufacturing capabilities rather than require new specialized capabilities. This isn't cost-cutting. It's a fundamental inversion of 150 years of weapons design philosophy. Guide Lamp Division's Anderson, Indiana facility becomes the model. Traditional firearms manufacturing requires experienced gunsmiths. The Thompson, for example, needs workers who understand hand-fitting precision components, a skill requiring months or years of training. The M3's genius is that assembly requires mechanical competence but not specialized firearms knowledge. The training timeline: workers receive 80 hours of instruction, 2 weeks before joining M3 assembly lines. Compare this to 6 to 12 months for Thompson production. The curriculum focuses on reading die specifications, operating spot and seam welding equipment, using assembly fixtures to maintain accuracy, and function testing rather than precision measurement. By late 1944, Guide Lamp employs over 3,000 workers producing M3S. Approximately 40% are women, unthinkable in traditional weapons manufacturing. Many have zero pre-war firearms experience. Some were housewives 6 months earlier. Now they're producing submachine guns that American soldiers are carrying into combat from Normandy to the Philippines. The psychological challenge is convincing quality control inspectors to embrace functional testing over precision measurement. Inspectors trained in traditional methods initially reject components that function perfectly but don't meet irrelevant tolerances. Retraining QC personnel to test "does it work" rather than "does it meet specifications" requires systematic institutional change. But it works. Rejection rates drop from 40% in mid-1943 to under 5% by early 1944. Complementary technological developments enhance efficiency beyond what pure labor scaling could achieve. Cold-swagged barrel production revolutionizes manufacturing. Traditional machining bores barrels from solid steel blanks, 4 to 6 hours per barrel, consuming expensive machine shop time. Guide Lamp implements cold swagging, forcing a 40-inch steel tube through progressive dies that reduce diameter while lengthening the tube and cutting rifling. A single 40-inch tube yields 5 finished barrels in 45 minutes total. This single innovation reduces barrel production time by 85%. Progressive die stamping evolves during 1944. Early M3 production uses single-operation dies, requiring workers to move components between multiple presses. By late 1944, Sampson's engineering team develops progressive dies, where one press stroke performs multiple forming operations sequentially. Receiver stamping time drops from 12 minutes to 4 minutes, while improving dimensional consistency. Automated seam welding eliminates the warping problems that plagued early production. Manual welding required skilled operators and created inconsistent heat distribution. Automated machines developed mid-1944 maintain consistent speed and heat input, virtually eliminating warping. Welding time drops from 8 minutes to 3 minutes per receiver. The combination creates exponential manufacturing efficiency. 1943's 7,000 monthly units becomes 1944's 28,600 monthly, a 4 times increase with only 2 times workforce expansion. Technology and training refinement account for the remaining gains. Battlefield statistics validate the transformation. Before M3 deployment in mid-1944, approximately 10% of infantry units carried submachine guns. By late 1944, that figure reaches 35% of frontline units. American soldiers have automatic weapons superiority in close combat that Japanese forces cannot match. Specific missions demonstrate M3 effectiveness. Operation Market Garden, September 1944, 82nd Airborne's M3 equipped units report 0 weapons failures during sustained combat operations in wet Dutch conditions. After-action reports note M3 reliability exceptional despite exposure to rain and mud. Battle of the Bulge, December 1944, tank crews equipped with M3S rather than Thompson's report faster egress from disabled vehicles due to compact size and lighter weight. Statistical analysis shows 67% survival rate for crews of disabled tanks equipped with M3S versus 61% for Thompson-equipped crews. 6 percentage points represents approximately 150 lives saved across the Ardennes campaign. Iwo Jima, February 1945, Marine Corps units report 40% reduction in weapons cleaning time compared to Thompson, enabling more time for combat operations in volcanic sand conditions that jam mechanisms relentlessly. The measurable success transforms procurement philosophy permanently. The M3's manufacturing approach influences post-war military development globally. The Soviet Union, studying captured American equipment through 1944 to 1945, recognizes the stamped receiver principle. When Mikhail Kalashnikov begins developing what becomes the AK-47, Soviet engineers explicitly adopt stamped construction. The initial 1947 AK uses a machined receiver, but by 1951, production shifts to stamped receivers, direct descendants of M3 philosophy. Over 100 million AK platform rifles have been produced since, the M3's conceptual grandchildren dominating conflicts worldwide. Japanese post-war industry learns different lessons from the M3. During American occupation, Japanese manufacturers study captured equipment and production documentation. They recognize that American mass production philosophy defeated Japanese craftsmanship. Companies like Toyota study American efficiency principles, eventually developing them into the Toyota production system that revolutionizes global manufacturing. The M3 becomes a teaching example in Japanese business schools. Crude but effective beats, refined but scarce. Post-war Japanese manufacturing excellence combines traditional precision with American production, efficiency, learning from defeat transformed into economic victory. Modern military's small arms universally adopt design for manufacturing principles pioneered by the M3. M4 carbine uses forged aluminum receiver optimized for CNC machining, different technology, same principle of designing for available manufacturing capability. Fen-Scar employs aluminum stampings and forgings designed for rapid production scaling. HKMP-5 features stamped steel roller-locked receiver, direct conceptual descendant of M3 stamped construction philosophy. Every modern military procurement request includes design for manufacturing requirements. The M3's legacy isn't just stamped receivers, it's the fundamental principle that weapons must be designed for how they'll be produced. Contemporary applications prove the principle's continued relevance. Ukraine's defense production expansion since 2022 explicitly follows M3 principles. Ukrainian factories convert automotive stamping equipment to produce anti-drone weapons, small arms components, and ammunition using design for manufacturing philosophy. Production ramps from 0 to thousands of units monthly in 18 months, the same transformation guide lamp achieved 1943 to 1944. Same principle, same results. 8 decades later. The universal lesson extends beyond weapons. Systems designed for how they'll be produced outperform systems produced to match ideal designs. This applies to software development, agile methodologies versus waterfall design, construction, modular building versus custom architecture, medicine, scalable public health interventions versus individualized treatment. Manufacturing, Tesla's design for production approach to electric vehicles, traces lineage to Hyde's 1942 insight. Modern military procurement officers study the M3 as exemplar. In 2024, U.S. defense analysts reviewing manufacturing efficiency for hypersonic weapons systems examine historical case studies. The M3 grease gun appears repeatedly, the gold standard for design for manufacturing philosophy. 82 years after Hyde sketched stamped receiver concepts, his insight remains foundational to effective military procurement. George Hyde never knew his legacy would span decades and influence billions of dollars in weapons development. He died largely unknown, his name absent from the weapons he designed. But every stamped receiver weapon produced globally, every AK-47, every modern assault rifle, every cost-effective weapon system designed for mass production carries his conceptual DNA. The final irony, Lieutenant Colonel Takeshi Yamada, examining the captured M3 in December 1944, understood he was holding proof of Japan's defeat. Not because the M3 was a better gun than the Type 100, it arguably wasn't in traditional craftsmanship terms. Japan lost because American engineers designed for the factories they had, not the factories they wished they had. Yamada survived the war. In 1952, working for a Japanese automotive manufacturer during post-war reconstruction, he attended a manufacturing seminar where Toyota engineers discussed lessons learned from American production methods. The lecturer displayed a photograph of an M3 grease gun as an example of design for manufacturing excellence. Yamada recognized it. The same crude stamped receiver. The same seam weld running down the side. The weapon that proved Japan's manufacturing philosophy obsolete. Except now, Japanese engineers were studying it not as an enemy weapon, but as a teacher, learning from defeat, transforming catastrophic loss into industrial renaissance. In the audience, Yamada understood something profound. The M3 hadn't just defeated Japan militarily. It had taught Japan and the world that the future belonged not to those who crafted beautiful weapons slowly, but to those who produced functional weapons rapidly. That lesson, purchased with hundreds of thousands of lives, became the foundation of post-war industrial civilization. Design for the capabilities you have, optimize for production. Function beats refinement. Scale beats perfection. Crude beats refined when crude can be produced 35 times faster. George Hyde sketched that truth in October 1942. The world is still learning from it in 2025.